Chapter 30, which is about inductance. Now we are going to here consider a new component, electronic component called inductor, which has an inductance. And we are going to look at how a time varying current, a current that is changing with time in one coil, can induce an EMF in the second, and like they are not connected. How to relate the induced EMF in a circuit to the rate of change of current in the same circuit, and the same circuit might induce a current in itself. How to calculate the energy stored in a magnetic field, how to analyze circuits that include both a resistor and inductor, and also we are going to study how and why electrical oscillations occur in circuits that include both an inductor and capacitor, and also we are going to end with having an inductor, resistor, and capacitor. Okay, you know, sometimes I don't know if you are aware of this, you're gonna find that you're going to reach a traffic light where all the other lanes are really nobody's waiting for the traffic light, and then your traffic light is gonna be green. This process works because we have a large coil that is placed under the street, and that has a current that is really changing with time. Of course, your car has conducting material, and then it's going to induce some of the currents, which is going to in turn induce an EMF in the coil that is underground. And that is really the principle for what we are going to study today. Here we have mutual inductance, which means like I have two coils. Here I have coil 1 and coil 2. And we can see that if the current in coil 1 changes, then this induces an EMF in coil 2 and vice versa. The proportionality constant for this pair of coils is called the mutual inductance. We will learn like how to calculate it, and we know like from Faraday's law that EMF 2 is gonna equal negative N2, the number of turns, times the rate of change of the flux. The mutual inductance is gonna be M equals N2, the number of turns, and then this is gonna have the flux in B divided by the current in phi B, which is the magnetic flux in 2, divided by the current from 1, because the current in coil 1 is the one that causes the flux through coil 2. And also in the same time equals N1 times the flux, the magnetic flux in 1 divided by the current in coil 2, because current in coil 2 is going to cause the flux through coil 1. The SI unit of mutual inductance is called the Henry, in honor of the American physicist called Joseph Henry. 1 Henry is 1 Weber divided by ampere equals 1 voltage multiplied by second divided by amperes. Like it has so many, equivalent units. Here I will say we have the electric toothbrush is working on the electric toothbrush makes use of mutual inductance. Its base has a coil that is supplied with alternating current from the wall, and then even though there is no direct electrical contact between the base and the toothbrush, this is going to induce an EMF in the coil within the toothbrush that is going to recharge the toothbrush battery. Now the self-inductance, any circuit with a coil that carries a current that is changing has a self-induced EMF. Here, for example, we have that coil here, and we're going to see that if there is a current going here through the coil, and if it is changing, okay, then the flux through the coil induces an EMF in the coil itself. We define the self-inductance L of the circuit as L equals and the number of turns times the flux due the current divided by I, which is the current in the coil. Now, inductors and lightning strikes, we're gonna find that, like you can see these near the, the power transmission systems or like lines. You're gonna find that these are really inductors there, that they are really incorporated into the transmission system so that they will suppresses any rapid changes in the current due to lightning. This circuit here, we are going to include them as elements in the circuit. And I will say here, if we have in this circuit, if we have that box here where we have a variable source of EMF, then the potential difference between the terminals of the inductor L is going to be VAB equals VA minus VB L times di over dt. Then the current here should actually change. If it is constant, nothing will happen. Now here we have, we're gonna compare the difference between having a resistor and an inductor. Here we have a potential across a resistor, and when we have the current going through the resistors from A to B, then the potential difference drops from A to B, and we're gonna have VAB equals IR, and that is greater than 0 because the current is gonna leave the high to the low. Now, if we have the same situation, but we have a constant current with an inductor, nothing, like we will not have any potential difference because VAB equals L di over dt, and then if di over dt is 0, then the potential difference is 0 as well. But if we have a potential difference across an inductor that is making the current increasing here, then I will say the current I is gonna flow from A to B. The potential drops from A to B. Therefore, the VAB L di over dt is gonna be greater than 0. And if we have, on the other hand, an inductor with decrease in current flowing from A to B, the potential difference is the potential increases from A to B, then the VAB L di over dt is going to be less than 0. Here we are going to talk about the also the how really comparing the two components, the resistor and the inductor. We're gonna say that a resistor in a device or in any circuit is gonna dissipate the energy, is gonna waste the energy, and we will not be able to recover it back. On the other hand, if we have an inductor, then energy can be stored in that and can be recovered whenever we need it. That energy stored in an inductor is going to be L times from 0 to I di, and that is 1/2 Li squared. I think when you look at it, you're going to find that it is really if we compare expressions, you're gonna find that there is a general I would say trend, or we're gonna talk about this in a little bit. The energy in an inductor actually stored in the magnetic field of the coil, very similar to how really the energy of a capacitor is stored in an electric field. And in vacuum, the energy per unit volume, which is called magnetic energy density, lowercase u equals b squared over 2 mu 0. And if we are going to have the magnetic field inside the material, it has like a different material, and then the permeability is going to be mu equals k magnetic times mu 0, and then we replace the mu 0 in the above equation by mu. Now this is a circuit that contains a resistor and an inductor, and we will say also we're gonna have an EMF source. And here when we close the switch S1, we're gonna connect the RL combination in series with the source EMF like here. Then we're gonna have a current going. And if we close switch S2 while opening S1, then this one is going to be open and this one is closed. This connects the combination from the source, and we're going to see how really this is working. Now this is when we close S1, and we're going to find that at t equals 0, we close the switch S1, and the current cannot change suddenly because of the inductor. It will, because of the self-inductance, and then it's going to go from 0 to some final value, but it needs time. As the current increases, the rate of increase of current given is going to become smaller and smaller, because finally that current is going to approach a final steady state value I, which is EMF divided by R. Now the time constant for the circuit, it is tau. Okay, very similar to tau equals RC. This is tau equals L over R for the inductor. And when T equals, tau equals L over R, we are going to find that the current is going to be I1 minus 1 over E. Now, suppose there is an initial current I0 running through the resistor and inductor shown in the figure. At the time t equals 0, we close the switch S2, bypassing the battery not shown. Okay, then the energy stored in the magnetic field of the inductor provides the energy needed to maintain a decay in current. And then the time constant for this also is going to be L over R, and then the current is going to decay. And I will say when we have tau, when we have the time equals L over R, which is tau, then the current is going to be I0 over 2. Now, what if we have L, an inductor with a capacitor? We're going to have oscillations. And then what does that mean? Here we have a capacitor that was completely charged here. And we are going to have 4 main steps of this oscillation. And here I will say in the LC circuit, that initial charge on the capacitor, it is Q maximum equals C V maximum. And we will then close the switch, and the capacitor, it is fully charged, and then the current, remember here we don't have an EMF in the circuit, the capacitor is gonna have first the current 0, and the circuit energy is all stored in the electric field of the capacitor. Then now the capacitor is gonna start discharging through the inductor, and as the capacitor discharges, the current increases, but the rate of change of current decreases till we will find that there is a potential difference that is going to be 0 in the capacitor, and the induced EMF is going to be also 0, and then the current has leveled at a certain value, maximum value, we call it IM. Now the capacitor has completely discharged and the current is maximal, and the circuit's energy is all in the magnetic field, which means it is in the inductance. Now Although the capacitor was completely discharged, the current persists and the capacitor begins to charge again, but polarity is going to be opposite. This is why we're going to say we have that oscillation. Eventually, the current and the magnetic field, they will reach zero, and the capacitor is going to be in charge with a maximum charge and opposite polarity. Shown in this situation, the capacitor is fully charged, and then the current is zero, and therefore the energy is all stored in the electric field, and then it's going to keep oscillating, repeats in the reverse direction. A little later, the capacitor has again discharged, and this is going to continue. The capacitor charge returns to its original value, and the whole process repeats again and again and again. We can apply here Kirchhoff's laws, loop rule to find the circuit shown, and this is going to lead to the charge here. It is actually changing in an oscillating sinusoidal expression. Q equals Q maximum cosine omega t plus phi, and I, the current, it is negative omega Q sine omega t plus phi, and the angular frequency of oscillation in the LC circuit is going to be omega equals square root of 1 over LC. We're going to see like how this is having a similarity with the simple harmonic oscillator. Then here, if you have a mass spring system, it is the kinetic energy, it is 1/2 mvx squared, and the magnetic energy for the LC circuit, it is 1/2 Li squared. For the potential energy, it is 1/2 kx squared, and here for the electrical energy, it is 1/2 q squared divided by c. Here, the conservation of energy, 1/2 m kinetic plus elastic potential energy equals the energy at the ends, and here it's the same 1/2 Li squared plus q squared over 2c equals q, the maximum squared over 2c. The current also I plus or minus square root of 1 over LC square root of q uppercase q squared minus lowercase q squared. I equals dx dq over dt, and omega, it is the square root of 1 over LC, and q is changing sinusoidal as q equals q maximum cosine omega t plus phi. Here we can have this arrangement, the LRC circuit, and here the EMF source charge the capacitor initially, and then the switch is moved to the lower position where we're going to have the LC circuit connected in series, and they are going to form that LRC circuit. Now the LRC circuit exhibits damped harmonic motion, which means the oscillation is going to be decaying, and the charge as a function of time is sinusoidal oscillation with an approximately decaying amplitude, and angular frequency is going to change. It's going to be omega prime equals square root of 1 over LC minus R squared over 4L squared. And of course, L is the inductance, C is the capacitance, and R is the resistance. Now I will stop here because I want to have another session for the problem solving.